Yeah.
Alright. Hi, and welcome again to Representation Learning. Today will be a little bit more theoretical lecture about mutual information and contrastive learning. So this will be kind of a departure from the autoencoder and denoising stuff from the last exercises. So let's get started. So one of the basic principles that we talked about in the first lecture that we want a good representation to have is consistency with respect to some transformations. So we have our image X, so could be image, could be anything else, and if we from there compute two transformations, x tilde 1, x tilde 2, so this could be a blurred version of the image or like a cutout. We will see examples of this later. Then we want, for a good representation, we want that g of, now let's write it small, that the representation stays invariant. So that's what we want. And now the idea is, basically, why don't we just enforce this directly? So what happens if we just do this? So we take some similarity measure that's high if the two numbers are vectors are the same, and low if they're different. Could be cosine similarity, could be something different. And we just maximize this. Or, well, we take the expectation over those transformed images, and then we maximize this for G. And then we basically directly enforce that two different representations have the same, the representations of two different transformations have the same representation. So, what would be the problem if we would just do this? Yes?
Well, it's not only one representation.
Yes, exactly. So, it could totally collapse. We could just make everything to one vector, then the similarity is always high. So invariance alone is clearly not enough, because then we lose a lot of information. So what at the end basically we'll do, we will take views, let's call them y1 to yk, or y tilde 1 to y tilde, and that are trafos of different images. So this one comes from the same image, and those are from k different images. And then we want to maximize this, but we want to minimize the similarity between x tilde 1 and the representation of g of y I, and then take the mean over I or something. So this is the rough idea. This is not like the loss that will end up at the end, but the idea is we want to maximize representation under transformations, the similarity of representation under transformations, but want to make every other representation different. So we want the contrast. That's why it's called contrastive learning. Okay, but to derive a better and proper loss function, we will view this in the information theoretical sense. So I already say, if we just do this, the problem is that we lose all information. So we want to lose some information. We want to lose all information that is not preserved by the transformations. So like pixel information that's like lost by rotating or whatever that we want to lose. but we want to keep everything else. So the proper one useful method for this is mutual information. So the goal is we want to maximize the mutual information between the representations. Okay. Are you all somewhat familiar with mutual information? Someone not at all? Okay. So the basic definition of the mutual information is if we have two random variables x with some density p of x and y with some density p of y, then the mutual information of x and y is defined as the integral of pxy times the logarithm of pxy divided by p of x and p of y dx dy, which is also equal to just the Kullback-Leibler divergence between the joint density, the joint distribution, and the product distribution. So we know that the product distribution and the joint distribution is equal if and only if the two variables are independent. And we know the KL divergence is only 0 if this is independent. So the important properties here are the mutual information is always greater or equal to 0, and it is equal to 0 if and only if x and y are independent. So if you listen to like the information theory course, you know all about this. Otherwise, I might see if I can find something online that you can read for some more background information. But that's like the important part that we want right now. So it's a matter of mutual, it's mutual information. And you can show that it's basically maximal if you can compute one variable from the other, but that's not so important right now. So this is what we want to maximize. The problem is we cannot even compute mutual information in general. So we cannot solve this integral. So we need to find some way to approximate it before we can maximize it. So this will be now the goal, to arrive at a particular estimate for mutual information called noise contrastive estimation, NCE, info NCE. Okay, so before we can maximize this, we need some way to approximate this. So now the next goal is estimate the mutual information between some random variable x and y. So at the end, x and y are going to be the representations of different transformations of images. But just for this sub-goal here, they could be any random variable. Okay. So this problem is symmetric. So one important property of mutual information is it's symmetric. So I of x, y is equal to the mutual information of y and x. But we will treat the problem as a little bit asymmetric at first. This has like historical context. So first they wanted to have like where x is the input and y is the representation, and they have a way to compute the representation from the input but not the other way around. But that's not so important right now. And at the end, the estimate that we get will be symmetrical again, but the thing in the middle won't be, you'll see. Okay. So the first estimate that I talk about is the estimate by Barber and Agakov, which I call IBA. And here the assumption is that this distribution is known, P of y given x, but P of x given y is not known, or it is, you can compute it. When we think about that x and y at the end will be representations of transformations of images, these assumptions don't really make that much sense, but let's just go with it for now. So in classical Bayesian variational methods, we will replace this unknown function with some variational distribution. So if you know like the derivation of the variational autoencoder, this is basically the same approach. So we approximate P of x given y with some variational distribution Q of x given y. Then we can write down the following. So we have the initial information, x and y. Now I'm just going to write down the definition again, P of xy times log of P of xy divided by P of x and P of y. And now we can extend this fraction by Q of y and x, y and x. And then pull everything apart, basically. And we get 3 terms at the end. The first one looks like this. So this is just an expectation, right? So this is just an expectation over this log term. So instead of the integral, I will write this as an expectation. We have the expectation of log Q of x given y. This is basically this term here. Then
Isn't it y given x?
Well, I wrote it down here wrong. It should be x given y. Thank you. Then we have minus the integral. Oh, that's right, that's an expectation again. How do I write this? Okay, minus the expectation given p, x, and y of log p of x. So this is this term here done, because it's in a denominator of the fraction, we put a minus here. And because there's no y in this term, we, instead of taking the expectation over px and y, we can just take the expectation over just p of x. And if you know a little bit about information theory, then you will see this is exactly the differential entropy of x. Okay, what's left? One second. One second. Why is this so strange? Why? Ah, right. Okay. So, short side calculation, p of x and y divided by p of y, of course, is just p of x given y. So this is just the definition of conditional probability, right? So then what's left is just the KL divergence between, not quite. Okay, what's then left is the integral of p x and y, which we can write as p of y times p of x given y. So this is equal to p of x and y, right? Times the logarithm of p of x given y. So then this here is gone. And q of x given y. And this is gone. Alright. And now we can dx dy. And now if we basically just look at this part, then this is exactly the Kullback-Leibler divergence between p of x given y and q of x given y. So the, god damn it. So the whole thing here is the expectation over p of y of the Kullback-Leibler divergence between p of x given y and q of x given y. Okay. So this is a different way of writing the mutual information between x and y for any probability distribution q. So it doesn't matter if it's actually a good approximation of the posterior, but this is true nonetheless. Okay, so now the Kullback-Leibler divergence, of course, is always non-negative. So if we just drop it, you get an equality. So then we have the mutual information is greater or equal to what was it? The expectation of log q x given y plus the differential entropy of x. And this here is our first estimate, the BA estimate. So this is a lower bound. We always want a lower bound, because then if you maximize this here, the idea is that you also will maximize the mutual information. But is this even a good bound? So can we achieve equality? Yes, we can. So the optimal Q, let's call it Q star, is just P of x given y. So if our variational distribution Q is exactly equal to this, then this correct Leibler divergence that we dropped is 0 and we have equality. So, but can we actually compute this? This term, the differential entropy, is problematic. So it is independent of Q, but we have to remember that learning Q is only a means to an end. So the idea is we first want to maximize this objective over Q to get a good estimation of the Michel information, and then we maximize it over our representation, which will change this here. But we can't usually compute this here, this integral, so this is not a very good estimate for our purposes. Okay, I of course I said now that we first compute, maximize with Q, and then we maximize over the representation, but in reality, of course, we will do both at the same time, exactly like with variation autoencoders. Okay, any questions so far, or have I completely lost you? Yes?
I wonder if X is now our images or representation, or is it like everything we want it to be?
So at the end, basically, it could be any random variable. Yeah. So, and if it's a distribution that's kind of like fixed, then this is a good estimate. But for our goals, at the end, X will be the representation of an image, or the representation of a transformation of an image. Okay. Now we will introduce the unnormalized version of this. So one problem besides this annoying differential entropy term is that we must maximize over this distribution Q. And learning a distribution is always annoying because we somehow need to normalize it. Because the distribution, a density must integrate to 1. So, and we can always represent it, probability distribution in a different way. And I think I will do it probably best if I use a different blackboard. So now the idea is we write our variation distribution Q using a so-called critic function f of x and y. And we just say Q of x and y is equal to, and I will leave a little bit of space here, you will see why in a second, e to the power f of x and y divided by zy, where zy is the expectation over q of x of e to the power x and y. Okay, so f of x and y can be any function. If we put it in exponential, it's a positive function, or a positive function. And we divide by this here, the so-called partition function, just so that this integrates up to 1. So you can, if this is known to you, you can think about f of x and y as like a negative energy function. But the basic idea is f is some function that measures how related x and y are. So if f of x and y is high, that should mean x and y are related. If it's low, it should mean they are not very related.
What do you exactly mean with related?
Generally similar, or like optimally in our case, it should only be high if there are representations from the same image, that come from the same image. If they share a lot of information. So, but now you can basically say, you can relatively easily see that you can represent any distribution in this way. I mean, we could plug this into our BA estimate back there, but this doesn't actually help us much. We just move the problem around. So now what we'll do, we will employ a little trick. We will scale this by p of x. Yes?
What is the word that you underlined before f of x?
Critic. And this will be useful because it will drop out the differential entropy, as you will see. Okay, so let's plug this into our BA estimate. My notes. So then we have the mutual information, not the mutual information. We have the expected value of f and, okay, how detailed do I want to write this? Okay, so log of q of x given y is then the equation of f of x. So log and e to the power cancels out. Plus log of p of x minus log of z of y. And for now the differential entropy term stays the same. But of course the differential entropy is just minus log p of x. And then the expectation over it. So this is the definition of the, well, together with the minus, definition of the differential entropy that we have there. And then this log p of x cancels out with this log p of x. And then what we are left with is the expectation of p of x and y over f of x minus the expectation over p of y of log z of y. So here we drop the x because there's no x in here. And this now we call the unnormalized BA estimate.
Sorry, why did we drop the y from the f function?
Oh, sorry. Yeah, there was a mistake on my part. It should be here, not this. Thank you. Okay. there's now just a slight problem with this, well, multiple actually. This inequality holds for any probability distribution Q of x given y. But if we define this way, this is in general not a probability distribution, because we scaled with the P of x here. If we didn't scale with P of x, it would integrate to 1, and this would be a probability distribution, but because we scale with the P of x, this is in general not a probability distribution anymore. But this is not a problem. Because when we think about what this integral is, integral of P of x given y dx. So by definition, this is the integral of P of x times E f of xy, z of y dx. Okay, and let's call this part for the time being, like, I know, q tilde of x and given y. So q tilde is a proper probability distribution because it integrates to 1. Q, in our case, we don't find generally not. But what we can do is apply the Cauchy-Schwarz theorem. So I don't know if you took analysis, you know it, otherwise Google it. Cauchy-Schwarz. It's maybe written with a T, I don't know. Let's write it. And see if this is less than or equal to the square root of the integral of P of x dx times the integral of q tilde x given y dx. So this is just a particular inequality that is sometimes useful. Of course, P and q tilde are now both probability distributions, so they both integrate to 1. So this is just 1. So this means that even though q of x given y is not a probability distribution, we can just scale it up with a number larger than 1 to get a probability distribution, and then we can basically use our inequality graph here. And so this too is also a lower bound for the mutual information. So if you wanted to write this like together, so let's say we have q tilde x given y, we define it as E of x and y divided by cy, and we define q of x given y as p of x times q tilde of x given y. Then the initial information of x and y is greater or equal to the BA estimate of x and y, and let's put like a q tilde here. So basically this estimate, if we plug in q tilde here, and this is then greater or equal to the BA estimate using our unnormalized function q, and this is then equal to our UBA estimate using our critic f. So now we still have a lower bound for our mutual information, but can this bound become tight? So can we achieve equality? And yes, this is relatively easy to see. So the optimal critic is given by log p of y given x plus some constant c of y, or some function that only depends on y but not on x. And in this case, we actually have equality here. So you can check if f has this form, if we plug it in here, then this term will be exactly equal to p of x given y, which we know is the optimal variational distribution. Okay, now comes the actual important part. Now, first, I want to rewrite this slightly. What we can do here, we can replace f of x given y by log of e to the f of x given y, and then put this together. So this is then equal to expectation over x given y. And then if we write out c of y again, just the definition, we get this here. Divided by expectation over, let's call it t of x prime. E of x prime y. So this is just a different way to write this. And this now looks awfully similar to the estimate that we'll see at the end. So again, basically, we push x and y together, the representation here with the numerator, and we push the representation of all the other pairs out with the denominator. So the question now is, how do we compute this? We could say we just replace this inner expectation by some empirical mean. So we just sample a batch of data and compute this here over the batch. And this is actually exactly what we'll do at the end. But the problem is that you can't just replace it and hope that the inequality still holds. Oh, I'm not missing a log actually, sorry. So, but just keep this formulation in mind for now. So this is a different way to write the UBA. But let's go back to this formulation. So here we have the expectation of this log partition function. And this is very difficult to estimate if you want to calculate this in practice. Because if we want to estimate with some kind of Monte Carlo estimation, we would first need to draw x to compute the inner, to approximate the inner expectation, then apply the log, and then draw from P of y to get the outer expectation. So we couldn't draw them together and just do Monte Carlo estimation. So what we will use now is a simple inequality, which is the following. Log of z of y is always less than e to the power minus 1 times z of y. And they're equal if and only if z of y is constant e. So if z of y is constant e, then of course it's equal. Then we have 1 on the left side, and log of e is 1, so it's equal. And to see that this inequality actually holds, you can just imagine like the graph of log x. So the graph of log x looks kind of like this, and it's concave. And log of e, of course, is exactly 1. And then if we imagine the line of the form ex is also e of e to the power minus 1 times x, which cuts the logarithm exactly at this point, and because of the logarithm it's concave, the line will always be above it. So this is why this holds. So we can use this approximation, plug it in, and we get our next estimate. So we have UPA of xy, and then if we plug in this estimate, we get this. And this is called the NWJ estimate from Wainwright and Jordan. Now, this estimate has the advantage that we could actually compute this just by Monte Carlo estimation. So just sample a bunch of px and p of y, but independently, and then just compute the mean of e of to the power f of x and y, f x and y. So we have again a lower bound of our lower bound, which is the lower bound of the other lower bound. But the question again is, can we achieve quality? Yes. So the optimal critic here is the form y equals to 1 plus log p of x given y and p of divided by p of x. So in this case, we can easily check if we integrate this basically that z of y is constant e. And in this case, we have equality here, and then this is equal to the UBA, and everything works out fine. And in this case, it's equal to the actual mutual information. Okay, so we have another nice estimate. The problem is that this term here has a very high variance. So you would need to sample very many x and y to actually get a proper estimate of this term. Now we introduce multiple samples. So let's say that you define x1 as just x, so we just rename it basically. And but we also introduce basically copies of x2 and xk, and they're all independently and identically distributed by the same distribution of p of x. And x1, xi is supposed to be independent of y for I greater or equal to 2. So the idea at the end is that x1 and y are representations of this that come from the same image, and x2 to xk are representations of completely different images. So these are independent of y. So then the mutual information of x1 to k and y. So I will write this basically as the joint variable x1 to xk is just equal to the mutual information of x1 and y, because x2 to xk are independent of y. Now we can plug this whole thing into our NWJ estimator, and we get the following. So this, of course, is still, the NWJ estimator still works here, of course. And if we write this out, and the optimal estimator, of course, optimal critic, then has the form 1 k and y. So here the critic takes x different, k different x values and the one y value, and the optimal critic has exactly the same form as there, is the same estimator. So it's 1 plus log of t of y given x1 to xk divided by t of y. But by our assumption, x2 to xk are independent of y. So this is really just equal to 1 plus log p of x1 given p of y. So why did we introduce x2 to xk anyway? So of course the optimal solution cannot depend on x2 to xk because as we already seen, in the optimal case we already achieve equality. The only thing that x2 to xk can help us with is reducing this variance from the Cartesian term. Okay, so now we know the optimal estimator must have this formula. And what's all so bad that our estimator now needs to take, instead of just two values, x and y, needs to take an arbitrary number of values. So we rewrite our estimator, our critic, using a simpler critic. So we want our critic that takes k different x values, and we write it using a simpler critic that only takes two values. And we'll do it like so. We'll just say f of x1 to k and y is equal to 1 plus log e to the power f of x1 and y divided by the hat of y of x1 to k. And the hat here is the Monte Carlo estimate of the Cartesian function. So the hat of x1 to xk is just the average over e of xi and y. Okay. Now, why does this help us? Now we can plug this formulation here into our NWJ estimator. So our so we have the expectation now not over just one x1 but x1 to xk and y of f of x1 to k and y minus e to the minus 1 of our z of y. So what I write it out, p of x1 to xk of e to the power and now we plug in this whole mess, and then we're basically done. Yes?
So I'm just wondering, you wrote f of x1 to xk and y, is that right? And then is that a different f there, or like
Yes.
the different functions? Or
Yes.
Okay.
I thought about giving them different letters, but
No, it's okay. I just didn't-
yes, they're different functions. So we have our function takes k different x values, and our function only takes one different x value. Okay. Now we plug this all in, and unfortunately I'm a little bit slow, I'm afraid, so I will skip to the end. Maybe I write the intermediate steps in the slides. Let's see. But what you will get at the end is this. So, the expectation of, where is it? P of, one second. P of y, we have an x1, so y and x1 are connected, the other x's are independent. Okay. Then here we have the log of e f times f of x1 and y divided by our z hat there, but I'll write it out. 1 over k, the sum of this e to the power f of xi and y. So here's x1 and y, and here's xi and y. And this is now almost our NCE estimate. Okay, so this is a special case of our MWJ estimate. So instead of saying we allow any function of this form, we say we only allow functions that have this form. So this is still a lower bound for the mutual formation, but can we achieve equality? And this time the answer is actually usually no. So if you see e to the power f x1 and y appears both in the numerator and in the denominator. So this whole thing here is always less or equal to 1. And then if we write a k around, this means the whole thing is always less than log k. And of course the mutual information of x and y can be much higher than log k. So if we assume that the representations of some images share, I don't know, have some 500 bits of representation information that we're interested in, if our k, which will be our batch size, is lower than 500, we can't possibly actually estimate the mutual information. So what we've done basically, we have reduced the variance of this term, but we introduced a bias. So if the k is too low, we can't possibly actually get a tight bound. So, and this now is, like I said, almost the NCE loss. The only thing what you need to do is introduce, instead of just one y, multiple y's. So for now we basically had x1 and y, which are paired basically. so not independent, and then x2, x3, and so forth. But now you basically introduce y2, y3, and so on. So that xy and y1 are not independent, but x1 or the other ones are independent. And x2 and y2 are not independent, but x2 and all the other ones are independent. And then we write this all together, and we get our NCE, noise contrastive estimation. And this is equal to the expected value of, what is it? One over k e to the power fxi and yi divided by this sum. Okay. So here on top we have xi and yi, and the bottom we have xi and yj. And this is the NCE estimator. And the thing is, if k goes to infinity, I didn't say how they're distributed, so x1 and y1 to xk and yk, they're all supposed to be IID from this k distribution. This equality actually doesn't work anymore if they are not independent, but it's important right now. So if k goes to infinity, this part here actually becomes a better and better estimator to our partition function, right? To the expected value of this. So as k goes to infinity, this actually becomes equal to the unnormalized BA estimator. So it's not there anymore, but for the UBA estimator I wrote down two different formulations. In this case it becomes unbiased. So the bias goes down as k goes up. So you definitely need to know basically this formulation, which is in the slides, and you need to know that as k goes to infinity, this becomes the UBA estimator. So in the original proofs, they basically just replaced this with the expected value and said this is equal to NCE, but this is not actually true. Okay. I think this was enough math for now and probably for the whole semester. So let's do some practical applications. I'll try to write down some of the proofs that I couldn't maybe do here, or I link to the source. I'd say you definitely don't need to know every details of the proofs for the exam, but at least some maybe. those I will write down nicer. Second. So there's an overview of the stuff we just talked about. I maybe add some more stuff to this. But you should, I think, know the proof of this bound where you just drop the KA divergence and of I'll decide that up. Don't have enough time. So now we need to go to SimCLR, which was like the first good use of this contrastive learning for representation learning on images. They were not the first that have done this, but the first that have done it in a somewhat nice way. So before I tell you exactly how they did it, here's some graph about the performance compared to other methods. Here top 1 accuracy on image set, like the classical evaluation for representation learning images. And here number of parameters, and we see SimCLR is better than all the rest. Almost as good as a tiny supervised model. And some of them here, like Moko, actually also uses contrastive learning, but they do it in a complicated way, which actually isn't so good. But next week you will learn about the successors of Moko. All right. Here we have the basic pipeline of SimCLR, as I talked about at the beginning. We take one image, x, we apply two transformations to get x tilde I and x tilde j. We apply some representations, and then, which is now a little bit different than we talked about before, we apply some other function g, which we call a projection head, to get z. And then we formulate our loss like this, where z is the sim is the cosine similarity. So this looks now very similar to the info NC, so let's make some comparison here. They call it NT-XN in the paper, but nobody calls it again after that, I think. So temperature normalized cross entropy or whatever. And basically, if we see sim of z, y, and j divided by tau, this is our critic. So they restrict the critic here further. Instead of saying we use any function of our representation. So the representation that we actually want to use at the end are called h, hy, and hj. Instead of saying basically the critic is any function, they say the critic is the scale, is the cosine product of those projections. So yeah, so they basically restrict what the critic can do further. And this is then basically equal to NCE, just the log 2n is missing. So this would be here the log 2n. Yes?
So in this one, they don't, on the sum on the bottom, you do it where k is not equal to I. Is that also, did you have that?
No.
It's different now?
No, it's actually not. So, that's actually an important point. Always. So in the NCE theory, we have our x1 to xk and y1 to yk. And in theory, they can be completely different things. So x1 could be representation of images and y1 could be representation of text, which we'll actually learn about later in the lecture. This then will be called not this lecture, later in the semester, which then will be called CLIP. And in the NCE laws, they only compute over the sum of E of xi and yj. So they only take xi and y1, x1 and y2, x1 and y3, and so on. Now in SimCLR, both x and y are representations of images. So they basically have one image, or they have n images in this case, n images, and each image leads to two representations, which they call here h1 and h2, and the next one will be h3 and h4, and at the end we have hn-1 and hn. And instead of only doing the contrast between h1 and h2 and h1 and h4 and h1 and h6, which is the uneven and even ones, they do the contrast between all of them. So they also do between h1 and h3 in this case here. But they don't want between h1 and h1 itself. So but this actually changes some things, because h4 and h3 of course are not independent, because they come from the same image. So this is not actually exactly info NCE, but again just another representation. And you can actually show that unfortunately, for some special cases, if you do it exactly like they did, is neither a lower nor upper bound for mutual information, but it still works. So if you wanted to do proper NCE, you only basically would use f of hi and hj, where I is even and where j is odd, but never two even ones together. So then this would be proper NCE, but they don't do this. If they would do this, then they would have the correct NCE, but then they would effectively only have like half the batch size, and well. So let's quickly go over the algorithm line for line. It's not actually very long. So we have our input f, which is our representation function. So this is what we actually want, f, which is what we want to learn. Then we have g, which is our projection head, which we basically use to compute our critic. And then with our set of transformations, which we'll talk about in a second, capital tau, I think that is. We get our n different images. For each image, we compute two transformations. X tilde with an even, with odd index, and x tilde with even index. And then we compute the representations, what we actually want, and then the projection. And then the cosine similarity between the projections will be our critic. Okay, then for every pair, they compute the critic. So basically, they compute the what we called before f of x, y, and yj. Put this all into this loss and take the average about it. Then they return f and throw away g. So the projection head, in the theory, is only used to estimate the mutual information, which is then used to maximize the mutual information. So the projection head is only like an auxiliary network, which you don't actually care about at the end. It's kind of like in a variation of autoencoder, if you want to use it for generative as a generative models, you only care about the decoder at the end and not about the encoder. It's just a means to actually train the encoder. And this is the same right here. So they don't quite see it this way in the paper, but this is basically just to help estimate mutual information. And this is to maximize the mutual information. Okay. What kind of images do they actually use? What kind of augmentations? They tested, I think, 6 different types or so. We have 10 different types, I don't know. Crop and resize. Just crop some square or rectangle and resize it to the original image. We have rotation, which we used already in the past. Cutouts, I mean, relatively self-explanatory, I think. Then crop, resize, and flip. Color distortion, Gaussian noise, a little bit blurry. Not blurry, but like noise, Gaussian blur. So just taking basically the average over neighboring pixels. Probably can't really see a difference on the beamer. Color distortion and the Sobel filtering. Do you know Sobel filtering? It's basically applying a specific kind of convolutional filter, like a handcrafted convolutional filter, to detect edges, which was popular back in the day when you had to do manual feature extraction. But the only augmentation that they actually use is crop, color distortion, and Gaussian blur, because they work the best. So in the exercise this week, we'll also play around with different augmentations to see which work and which don't. They did a big ablation study with all combinations of the augmentations. So basically, they applied 2 different types of augmentations and took every possible combination and evaluated the trained network with linear probing on ImageNet. So in the diagonal, they only use one type of augmentation. So here they only use crop, here they only use cutout, and so on. And we quickly see that some of them are much better than other ones. Especially the crop seems to be very useful. So the combination of crop and color especially yields a high result at the end. So, or color and crop. So this is just a difference if I did crop before or color before, so I don't know why it is actually different. Who knows? And some just don't work, like just blur is of course not nearly enough. You need especially sometimes cropping. So, and one of the ways that they saw that especially color and crop is important is they did some color histograms. So you see here, crop is good, but the biggest jump is basically if you do crop and color. Crop without color doesn't work so well. So this is the biggest takeaway about the augmentations. So there are some color histograms. They took the color intensity for each pixel and put it in a histogram. So we have 4 things here. We have 2 different images. The top row corresponds to one image, the bottom row corresponds to another image. And how we want to read this is, these are the color histograms of different cutouts, of different crops of the same image. And we see they're all very similar. So if we crop the image at different places, the color histogram will basically stay the same. And this is true for most images. Of course, if you do a crop where you only crop like the green grass here, you will get a different color histogram. But on average, the color histogram tends to stay the same. And there's a lot of easily learnable information in this color. So our representation network will only basically learn this color information. So we destroy it with color distortion. And then the color histograms are not the same anymore. So it's basically something called shortcut learning, where the network just learns some easy way that 2 images are the same. But of course, we don't want to just learn the color histogram. We can compute this ourselves. So that's why color distortion is especially important, because a lot of unwanted information in color that we need to throw away. Okay, what else? Yes. What we saw before. Our info NCE loss. To be good, it needs 2 things. We need an expressive critic. So this only works if our critic here can mimic any function, and we need a large batch size. Because otherwise, like I said, our estimate is highly biased. So they do exactly both these things. They use a large batch size, and they use a large projection head, which then corresponds to an expressive critic. So here they did a lot of ablation studies about different batch size. Here the x-axis are different training epochs, and we see that longer learning always helps. On the y-axis are, on the one hand, just the top 1 accuracy, and the color in the bars indicates the batch size from left to right. So the smallest batch size they tried is 256, which is already not so small, but they see that we really need at least a batch size of 1024 when training on ImageNet to do any good training. And this is with contrastive learning generally a big challenge to get like train with high enough batch size to overcome this bias. And there are some ways to do this. You can use like exponential moving average, which we will learn about next week. But for now, it's important to know contrastive learning needs a high batch size. They also did some ablation studies about the projection head, which mimics our critic from earlier. They checked just the linear layer, non-linear, network, so an MLP with a single hidden layer, and no projection head basically, just direct cosine similarity. This corresponds then here to something where f has no learnable parameters. And it turns out if we have a nonlinear projection head, so an MLP with a hidden layer, with a large dimension at the end, then we get good performance. Because this corresponds to an expressive critic, so we get a good estimate of the mutual information. And that's basically it. So that's the takeaway here is that contrastive learning maximizes mutual information, approximately enough. And then you could talk about, is this even a good idea to maximize mutual information? There are some people that say, no, not really, but that's another topic altogether. But to actually train it, you need the right augmentations with a large batch size and a somewhat large projection head. And that's it for this week. Thank you.